Okay, so we're taking a look at another one of our sample problems, and in this case, oops, I need to scroll down a little bit on my computer here so I can actually double check this stuff. Let's see, yep. Okay, this one's a little bit of a longer one, and it's motion in multiple parts. A record of travel along a straight path is as follows. So we've got some compound motion here. We've got an object that's starting here at the very beginning. We could call this some position x0, and we'll call that 0. Now, I'm going to split this into sections here. Let's see. It says, start from rest with constant acceleration of 2.37 meters per second squared for 17.5 seconds. So here's what we've got. We've got some motion where it goes forward like this to some other point. We could call this x1. And during this period, we are told the following. Delta x, v final, v initial, acceleration, and time. We are told that it starts from rest, so that's 0 meters per second for our initial velocity. Our acceleration for this period is 2.37 meters per second squared, and the time for this is 17.5 seconds. Okay, great. Then, after that, they go at a constant velocity. We'll go ahead and do this with blue. They're moving forward, constant velocity of, let's see, delta x, v final, v initial, acceleration, and time. They told us it's a constant velocity, so we've got 0 meters per second squared for our acceleration. And they tell us that the the speed at which they're moving, their velocity, is 41.475 meters per second. And since it never speeds up or slows down during this section of motion, the blue section, that would be both our beginning and ending velocities, our initial and final. Okay, and they do this for the next 0.978 minutes. 0.978 minutes, which I'm going to take a moment and go ahead and convert that now. So 0.978 times 60, and that gives us that is a time period of 58, sorry, it's been a long day, 58.68 seconds. Okay. And then finally, they say, for the final section, we'll do this with purple, I guess. I'm going to mark question mark because on this one, they say that they're subjected to a constant negative acceleration, delta x, v final, v initial, acceleration, and time. We have an acceleration of negative 8.92 meters per second squared. So initially, since this thing is moving forward and it has a negative acceleration, it's going to begin to slow down. Its acceleration will become more negative. So it'll start by slowing down, but we don't know. It may actually go long enough that it slows down, comes to a stop, and starts moving the opposite direction. So, something for us to think about. We might have it where this starts backtracking some, and we might even end up way back over here. We'll find out. Constant negative acceleration of negative 8.92 meters per second squared for 4.13 seconds. 4.13 seconds. I'm going to find that unlikely since in the middle section it was actually traveling for almost a minute. I have a hard time, although we'll find out, I have a hard time thinking that it's going to backtrack all that way in only 4 seconds, but we'll see. And the question is, what was the total displacement for the complete trip? Now in this last section, we know that it's coming from the blue section, so at the beginning of it, the object must have been going 41.475 meters per second. And we don't know how fast it's going at the end of the purple section because it does have a non-zero acceleration, so it will speed up or slow down. In this case, it's going to start slowing down, but it might eventually speed up. Depends on how our numbers work out. What they're looking for is our total delta x. So let's look at our displacements for each section, and if we can find those, we should be able to add them up to see where we are total. Okay, well, that gives us a pretty good idea. Let's double check here in the red section. Now the main thing I'm after is the displacement, so I'm going to use the equation that does not have the final velocity. So that's delta x equals v naught times time plus 1/2 at squared. I'm going to fill this in. Hopefully you've seen quite a few of these now. I'm going to go a little bit lighter on the units. We've got delta x equals 0 goes in for our initial velocity, so we have just 0 for our first term, plus 1/2 a is 2.37 meters per second squared, times t squared, which is 17.5 seconds, quantity squared. I'm going to go through and try and solve this. So we've got 17.5 squared times 2.37 times 1/2. And if I've done this correctly, delta x comes up to a positive 362.9 meters. I'm going to go ahead and keep 4 significant figures. Sometimes these systems get a little bit picky when we're adding and subtracting stuff. So in this case, I recommend sticking with 4 significant figures just to be safe. You'll most likely get an answer that the computer recognizes with only 3, like we usually use in class. But I've noticed before, since we're going to need to add these up, sometimes it can get a little bit tricky. So 362.9 meters. I'm going to check something real quick. The final velocity, which I could do by ignoring delta x and use v final equals v initial plus at. I'm going to check that real quick. 2.37 times 17.5. And we end up with, yes, you're welcome to double check this, but we do end up with a final velocity in this section based on its numbers of 41.475 meters per second, which makes it agree with the blue section. I was going to be worried if it didn't, but let's use the numbers that we've got there. The big thing we need is delta x. That's what we want, because that's going to get us closer to our solution. Okay, now let's look in the blue section. Well, we've got just a whole bunch of information, so I'm just going to use pretty much the same equation. We just need to use one that has delta x in it, and given a little bit of knowledge that I have because of how the 0 is going to work, we're also going to need to include the time. I'm going to go with equation number 2, delta x equals v naught times time plus 1/2 at squared. Well, delta x will be equal to, our initial velocity for this was 41.475 meters per second times 58.68 seconds plus 1/2. Our acceleration this time in our second section is 0, and then we would be times time squared, which is 58 whatever squared, but we don't have to care because since acceleration is 0, all those things that are multiplied by it just become 0. So we get the following, 41.475 times 58.68, and we get that our displacement in the blue section is a whopping 2,434 meters to 4 significant figures. So I'm going to write that up here. We get 2,434 meters. Okay, our last section is the purple section. Once again, we don't know the final velocity on this. That's okay. That's not something that we're actually interested in, but that does tell us that we're going to continue using our second equation. Delta x equals v naught times time plus 1/2 at squared. Okay. Delta x is what we're after. Our initial velocity, we said, was 41.475 meters per second at the beginning of the purple section, times our time, I believe it was 4.13 seconds, plus 1/2, our acceleration was negative 8 something, I think, negative 8.92 meters per second squared, times time squared, which was 4.13 seconds, quantity squared. I apologize, I'm running out of space there. Okay, I probably could have brought the whole thing over. My apologies. Delta x is therefore equal to, we're going to go 41.475 times 4.13, and we end up with our first term here is 171.29, we'll call that 171.3, and this is meters per second times seconds. The seconds cancel out, so we've got meters, plus 1/2 times, let's see, I'm going to take 4.13, I'm going to square that, that's going to give me time squared, times negative 8.92, that's going to be negative 152 and some change, and then I'm going to multiply that by 0.5, or 1/2, and we get plus a negative 76.07 meters. Okay? That's what this should come up to. Our second squared cancels out with our divided by second squared, and we get this. So I get 171.3 plus a negative, or minus 76.07, or we could say 76.1. And we get the following. That delta x for our purple section is 95.23 meters. Okay, now that's a bunch of work, but that is not our answer. That's how far it went in the purple section. So we did come to a stop and backtracked a little bit on the purple, but we did not actually backtrack on the blue or the red based on the times involved. So now, to find our total displacement, we just need to add up all of our individual displacements. So I'm going to take the 95.23, and I'm going to add that to 362.9, and I'm going to add that to 2,434, and I get something in the ballpark of, when I add up all of our delta x's, I get delta x total of 2,892 meters. Technically 0.13, but 4 significant figures should be fine. Double checking, I've got 2,891.88, in other words, 2892. That is the answer that they have listed. This one's a very challenging problem and not the sort of thing that we would ask you on a test unless it was a larger free response section. We'd probably split it into sections like solving the red section, then solving the blue section, then solving the purple section, that sort of thing. So it's not likely to be given to you as one giant problem, at least on our tests.